Good morning to everyone. Today we will discuss about the concept of magnetism and matter. In this magnetism and matter, it is very easiest chapter for IPE as well as objective orientation. So, what is a magnet and what are the types of magnets? What is magnetic property and what are the properties of the magnets? Let us discuss one by one in this class. First one, magnetic phenomena. You know very well, Earth is also a huge magnet. Magnetic phenomena are universal in nature. So, long before, some scientists observed that iron ore called magnetite, Fe3O4, it is found in magnesium, has the property of attracting small pieces of iron, steel, cobalt, nickel, etc. The iron ore showing this property of attraction was named as natural magnet, and the study of properties exhibited by these magnets was termed as magnetism. Later, the iron ore is suspended freely in the Earth's magnetic field. It always aligned itself along the north and south directions of Earth. Because of this property, the iron ore was called as lodestone or loading stone. But the shape and size of the natural magnets, they are very irregular, and also their magnetism is also quite weak. That's why they are generally not used. But some artificial magnets are widely used in various electrical appliances. So, this is only, all this concept is the only introduction about the magnetism. Leave it. In general, any substance, it is remembered that any substance which exhibits both attractive property and also directive property, then it is known as a magnet. Attractive means it attracts small pieces of iron, cobalt, nickel, etc. Directional property means when it is suspended freely in the Earth's magnetic field, it always aligns in the direction of north and south of Earth. It is called directional property. So a substance which obeys these two properties, then it is called as a magnet. Now, what are the types of magnets? First one, natural magnets. Natural magnets means iron ore which is known as the magnetite, like Fe3O4. It is taken as the natural magnet. But by some artificial methods, some magnets are made which are used in the electrical appliances. They are called artificial magnets. But it is remembered one point, Earth also behaves as a magnet with magnetic field pointing from geographic south to north. This one important. Earth magnetic field is taken from geographic south to north. Yes. So next one, what is meant by a bar magnet? Depending on the shape as well as size, magnets are of so many types. Bar magnets, horseshoe magnets, and also concave shaped magnets, and so on. First one, bar magnet. Bar magnet means it is in the form of a rectangle like this. It is said to be a bar magnet. So, it is in the shape of a rectangle. Thickness is very less when compared with the length. What are the properties of the magnets? Suppose Let the bar magnet which is completely immersed in the iron filings. Iron filing means it is a small iron pieces. Small iron pieces, they are called iron filings. When the bar magnet is completely immersed inside the iron filings, it is observed that more iron filings are concentrated at the ends of the magnet. That's why the total magnetic property or attractive property concentrated more at the ends of the material or at the ends of the magnet. So they are called as the poles of the magnet. Poles of the magnet. Next one, directional property. When it's suspended freely in the Earth's magnetic field, the magnet align in the direction of north and south of the Earth. So, the pole of the magnet directed towards the geographic north is known as the North Pole, and the pole of the magnet directed towards the south of the Earth is known as the South Pole. So that's why any magnet has two poles. One is North Pole, second one is South Pole. Next one, what is meant by magnetic axis? Magnetic axis means it is a straight line joining the north and south. A straight line joining the north and south of the Earth and also passing through the center of the magnet is known as the magnetic axis. So, how do you define the magnetic length as well as geometric length, and what are the relation between magnetic length and geometrical length? Suppose, let us take one iron rod. Length of the soft iron is equal to, length means it is nothing but the shortest distance from, actual length from one end to another end of the iron rod is known as the geometrical length. When this iron rod is made to a magnet, there are so many methods, by single pole method or by electrical conduction method and so on. So, the soft iron is made as a magnet. Magnet means it has two poles, south and north. Once again, these two poles are the unlike poles, and there should be a force of attraction between these two. That's why north and south poles, they are not formed exactly at the end. They are formed just beyond the edge. Now the shortest length from south to north is called as the magnetic length, and magnetic length is represented by 2L. It is always taken as a vector quantity. It is taken or measured from south to north along the axis. It is remembered that 2L bar, it is a vector. It is called as magnetic length. But clearly from this diagram, which one is more here? Either geometrical length or magnetic length? Geometrical length is more compared with the magnetic length. Okay, na? Right. Now the relation between magnetic length and geometric length is, magnetic length is equivalent to 5/6 times the geometrical length. It is the experimental result. That means, in terms of percentage, 83% of the geometrical length. That means, suppose an iron rod of length 100 centimeters is made as a magnet. Its magnetic length is approximately 83 centimeters. Right. Next one, what are the laws of magnetic poles? First one, any magnet which is having two poles, North Pole and South Pole. The two poles of a magnet have equal strength and opposite in nature. Means equal strength. Equal strength means both the poles attract the iron pieces by the same amount of energy or by the same amount of force. But their nature will be opposite. Next one, unlike poles attract each other as well as like poles repel each other, similar to electricity. Isolated poles are not possible. Isolated poles means, suppose this is a long bar magnet. It has two poles, north and south. Let the bar magnet is cut into three pieces like this. Three pieces. Each piece also behaves like a thin magnet, like S and N, S and N, S and N. Even if these three pieces are also cut into two equal halves, Each and every piece also having two poles, that means one dipole, magnetic dipole. That's why the two poles of the given bar magnet cannot be separated or cannot be isolated always. Next one, pole strength means it is the pole of the magnet. So the ability of the pole which can attract the surrounding magnetic materials is known as the magnetic pole strength. For example, small iron needle is kept very near to it. It is attracted towards the north pole. If the pole is very strong, it is strongly attracted towards the pole. That's why the ability of the pole which can attract the iron needle or iron materials towards it indicates the pole strength. Mari, this pole strength depends on what parameters? First one, pole strength small m depends on nature of the material of the magnet, area of cross section of the material, area of cross section of the pole. It is one most important concept. And level of magnetization means if the given bar magnet having more magnetic property, its pole strength is also more. Right. Pole strength independent on shape of the magnet. It does not depend on shape of the magnet. Either it is bar magnet or horseshoe magnet, whatever it may be. It is independent. Depends only on area of cross section of the pole. And pole strength is a scalar quantity and its SI unit can be written as ampere meter. Remember this. How this ampere meter is the unit for pole strength that is explaining in moving charges and magnetism. Right? So this is the concept about the pole strength. Next one, how do we define the magnetic moment? Magnetic moment can be defined as it is nothing but the product of pole strength and length of the magnet. Pole strength small m, length of the magnet 2L bar. 2L bar is a vector, that's why m bar is also a vector. 2L bar is always taken from south to north along the axis. So capital M is also along the direction of length. So m is a vector quantity and it is directed from S to N along the axis. SI unit is equal to ampere meter square. Why it is ampere meter square? Pole strength is represented in ampere meter, length represented in meter. Ampere meter into meter, ampere meter square. This is the concept about magnetic moment. Next one, suppose a bar magnet is cut into number of pieces. What happens the pole strength, length and also magnetic moment of each part? First one, cutting off a bar magnet. This is the original bar magnet and length of the bar magnet is equal to 2L. Pole strength of the bar magnet is equal to M, magnetic length 2L. Magnetic moment is equal to capital M is equal to small m into 2L. Let this bar magnet is cut into two equal parts like this. Ela cut chesamankondi. Ela cut chestunam. If it is cut into two equal parts parallel to its length, cut into two equal parts parallel to its length. While cutting the magnet along the axis, area of cross section of the pole becomes half. Area of the pole becomes half. Area half means pole strength also becomes m by 2 because pole strength directly proportional to area of cross section of the pole. Length of each part is same. This one length 2L, this one length 2L. Magnetic moment of each part m dash is equal to m by 2 into 2L. But m into 2L is equal to capital M, original magnetic moment, by capital 2. That's why m by 2. So, a bar magnet is cut into two equal parts parallel to its length. Magnetic moment of each part becomes m by 2. In the same way, let the bar magnet is cut into n equal parts parallel to its length. N equal parts parallel to its length. And pole strength of each part is equal to m by n because m is proportional to A. And this is the area, while the pole and magnet is cut into n parts like this. Area of cross section becomes 1 by n times. Pole length also becomes 1 by n times. Length of each part remaining 2L. So the magnetic moment M dash is equal to M by N. Let the magnet is cut into two equal parts perpendicular to its length. Magnet is cut into two equal parts perpendicular to its length like this. And this is the length. It is cut into two equal parts like this. While the magnet is cut into two equal parts, there is no change in area of cross section of the pole. Means pole length remaining same. But length of one part is equal to half of the total length. Means 2L by 2. Magnetic moment of each part M dash is equal small m into 2L by 2. Small m into 2L is equal to capital M original magnetic moment by 2. So in the same way, the magnet is cut into n equal parts perpendicular to its length. Pole length remaining same. Length of each part 2L by n and magnetic moment M dash is equal to M by n. This is the concept about the cutting of the magnet into number of pieces. Next one, resultant magnetic moment. Resultant magnetic moment due to combination of magnets. So here let us consider two bar magnets. Magnetic moment of the first one is M1 and for the second one is M2. The two magnets are contact at one end such that like poles are contact together. Yes and yes. But you know very well, magnetic moment is a vector. Its direction is taken from S to N. M1 this. And this is the M2 for the second magnet. Angle between these two magnets is given by theta. According to parallelogram law of vectors, resultant of these two is equal to root of M1 square plus M2 square plus 2M1 M2 cos theta. But in the another example, maybe the two bar magnets are placed in contact at one end such that unlike poles are kept in contact. This is N for the first magnet, this is S for second magnet. Angle between them is theta. Here the direction of first magnetic moment is M1. For second magnet of moment is M2 like this. This is the angle theta. And angle between M1 and M2 is equal to 180 minus theta. Therefore, M dash equal to root of M1 square plus M2 square minus 2M1 M2 cos theta. Minus. Why it is minus? M1 square plus M2 square plus 2M1 M2 cos of 180 minus theta. Cos 180 minus theta is equal to minus. Okay, na? This is the formula for resultant magnetic moment. This is the formula for resultant magnetic moment. Suppose in both the cases, both the magnets having same moment. If M1 equal to M2 equal to M. In the first case, M dash is equal to M square plus 2M cos theta and 2M square cos theta. 2M square into 1 plus cos theta. 2M square into 1 plus cos theta and 2 cos square theta by 2. Therefore, M dash is equal to 2M cos theta by 2. This is the formula for net magnetic moment. And here, in the second case, root of M square plus M square minus 2M square cos theta. 2M square common here, 1 minus cos theta. 1 minus cos theta means 2 sin square theta by 2. On solving it, M dash is equal to 2M sin theta by 2. It is remembered that both the examples, when like poles are contact together, M dash is equal to 2M cos theta by 2. Unlike poles are kept in contact together, M dash is equal to 2M sin theta by 2. When it is possible, when both the magnets are identical, having same magnetic moment, remember this formula while doing the problems. Next one, here there is one example. Let us consider two identical bar magnets. First, they are arranged in the form of plus, in the form of letter T, in the form of L. Here, these are the two magnets. It's the direction of M. It's the direction of M for the second magnet. M and M both are perpendicular to each other. Theta becomes 90. Cos 90 is equal to 0. That's why M dash is equal to root of M square plus M square. Root 2 into M. Here also, M and M, angle between them is 90. Resultant is also root 2M. Here also, m and m, angle between them is 90, resultant is also equal to root 2 into m. This one very important. Next one more example. Let us consider four identical bar magnets, each of magnetic moment m. They are arranged to form a square. Find the net magnetic moment. Here, let us draw the directions of magnetic moment of each and every magnet. Here, this is the direction of magnetic moment of the first magnet, m. This is for second one. And this is m to n. This is s to n, m. This m and this m both are equal and opposite. Resultant is equal to 0. This m and this m both are equal and opposite. Net equal to 0. So, a resultant magnetic moment m dash is equal to 0. Here, all these magnets are arranged in the form of a square such that unlike poles are kept in contact at any side. You try one example. If all these four bar magnets are arranged such that their like poles are kept in contact, find the value of resultant magnetic moment. In that situation also m dash is equal to 0. Next, second example means three identical bar magnets each of moment capital M are arranged to form a equilateral triangle. Find the net magnetic moment. While doing this, there are two methods. One is vector method and second one is logical method. So this is first magnet S to N, M, magnetic moment. It is along positive x direction. Here this is x, y. M1 bar is equal to m into I bar. M2, it is lying in a plane. M2 is also m. This makes an angle 60 degrees with x-axis. That's why m is resolved into two perpendicular components. Along this direction m cos 60, along this direction m sin 60. So m2 bar is equal minus m cos 60 because it is along negative x-axis, minus m cos 60 I bar plus m sin 60 j bar. That is minus m by 2 I bar plus root 3 by 2 m j bar. The third one is, it is like this, m. It also makes an angle 60 degrees. Here this is 60, this is also 60 degrees. M will also resolve into two perpendicular components. This is m cos 60 and m sin 60. So m3 bar is equal m sin m cos 60, it is along negative x-axis, minus m cos 60 I bar. This is along negative y-axis, minus m sin 60 j bar, minus m by 2 I bar.